Welcome to DAR Tutors, your home for online and home tuition. In this video, we will explore two important applications of differential equations that are key to the IB mathematics analysis and approaches higher-level curriculum. First, we'll tackle problems involving tangents to curves, which often lead to separable differential equations. Second, we'll dive into logistic growth, a powerful model for populations with limited resources. By the end of this session, you will be able to formulate and solve differential equations from geometric descriptions and apply the logistic growth model to real-world scenarios. Let's begin. Our first objective is to learn how to find the equation of a curve when given a geometric property of its tangent line. This involves translating the geometric information into a differential equation. Let's look at our first example. Consider a curve in the first quadrant. The tangent at any point P on the curve cuts the x-axis at a point Q such that the distance from the origin O to P is equal to the distance from P to Q. We are also given that the curve passes through the point 1, 4. Our goal is to find the equation of this curve. The first step in these problems is always to visualize the situation. Let's draw a diagram. Here's our coordinate plane. We have the origin O at 0, 0. Let's pick an arbitrary point P on the curve in the first quadrant and label its coordinates as x, y. Now we draw the tangent line to the curve at point P. This line intersects the x-axis at a point Q. The problem states that the distance OP is equal to the distance PQ. This is the key piece of information. The fact that OP equals PQ tells us something very specific about the coordinates of Q. Let's use the distance formula. The distance OP is the distance from 0 to y to down to mal to hack y, which is the square root of x squared plus y squared. The distance PQ is the distance from outside xy to q squared to q now, where q is the x-coordinate of q. This is the square root of q minus x squared plus y squared. Since OP equals PQ, their squares must also be equal. This gives us x squared plus y squared equals minus x squared plus y squared. The y squared terms cancel out, leaving us with x squared equals q minus x squared. Taking the square root of both sides, we get x equals plus or minus q minus x. Since p is in the first quadrant, x is positive. From our diagram, q is to the right of p, so q must be greater than x, which means q minus x is positive. Therefore, we must take the positive root. X equals q minus x. Rearranging this gives us q equals 2x. So the coordinates of q are 0. Now that we have the coordinates of p and q, we can find the gradient of the tangent line PQ. Remember, the gradient of the tangent is given by the derivative di dt dx. The gradient of the line segment PQ is the change in y divided by the change in x. This is y minus 0 divided by x minus 2x. Which simplifies to y divided by negative x or negative y over x. Since the line PQ is the tangent to the curve at P, its gradient must be equal to the derivative of the curve at that point. Therefore, we have our differential equation. Dx equals negative y over x, div y habitai. This is a separable differential equation. We can solve it by separating the variables and integrating. Let's rearrange the equation to get all the y terms on one side and all the x terms on the other. We get 1 over y times dy equals negative 1 over x times dx. Now, we integrate both sides. The integral of 1 over y with respect to y is the natural logarithm of the absolute value of y. The integral of negative 1 over x with respect to x is negative the natural logarithm of the absolute value of x. Don't forget the constant of integration, c. We can simplify this expression using logarithm properties. Adding ln x to both sides gives ln x plus ln y equals c. Using the product rule for logarithms, this becomes ln xy equals c. To eliminate the logarithm, we exponentiate both sides. This gives us the absolute value of xy equals e to the power of c. Since e to the power of c is just another constant, we can call it k, so we have xy equals k. We're almost there. We have a general solution, but we need to find the specific value of k for our curve. We can do this using the initial condition. The problem states that the curve passes through the point 1, 4. This means when x is 1, y is 4. Substituting these values into our equation, we get 1 times 4 equals k, so k equals 4. Therefore, the equation of the curve is xy equals 4. We can also write this as y equals 4 over x. This is the equation of a hyperbola. We have successfully translated a geometric description into a differential equation and solved it to find the curve's equation. Let's try another example of this type to solidify our understanding. This one involves a ratio, which is a common technique in IB problems. The tangent at any point P on a curve cuts the x-axis at A and the y-axis at B. We are given that the ratio of the distance AP to the distance PB is 2 to 1. The curve passes through the point 1, 1. We need to find its equation. Again, let's start with a diagram and define our points. Let P be the point, xy, on the curve. The tangent line at P intersects the x-axis at A and the y-axis at B. The ratio AP to PB is 2 to 1. The ratio AP to PB being 2 to 1 means that P divides the line segment AB in the ratio 2 to 1. We can use the section formula to relate the coordinates of PA and B. Let the coordinates of AB A0 and B be 0B. The section formula states that the coordinates of P are given by this expression. Substituting our ratio mx2 and n1, we get that the x-coordinate of P, which is x, equals 1 times a plus 2 times 0, all divided by 3. This simplifies to x equals a over 3, so a equals 3x. Similarly, the y-coordinate of P, which is y, equals 1 times 0 plus 2 times b, all divided by 3. This simplifies to y equals 2b over 3, so b equals 3 over 2. So we have found the coordinates of the intercepts in terms of x and y. A is 3x, 0, and b is 0, 3y, 2. Now we can find the gradient of the tangent line AB and set it equal to y. The gradient of AB is the change in y over the change in x, which is 3i2 minus 0, divided by 0 minus 3x. This simplifies to negative y over 2x. Since this is the gradient of the tangent at P, we have our differential equation. d/dx equals negative y over 2x. This is another separable differential equation. Let's solve it. Separating the variables gives 1 over y di equals negative 1 over 2x dx. Integrating both sides, we get ln y equals negative 1/2 ln of x plus c. Let's simplify this using logarithm properties. We can move the negative 1/2 inside the logarithm as a power, giving ln y equals ln n x to the power of negative 1/2 plus c. Rearranging, we get ln y minus ln x to the power of negative 1/2 equals c. Using the quotient rule for logarithms, this becomes ln y divided by x to the power of negative 1/2 equals c. This is the same as ln I times the square root of x equals c. Exponentiating both sides, we get y times the square root of x equals k, where k is a constant. Squaring both sides gives y squared times x equals k squared. Since k squared is just another constant, let's call it c. So our general solution is y squared times x equals c. Finally, we use the initial condition to find c. The curve passes through 1, 1. Substituting x1 and y1 into our equation, we get 1 squared times 1 equals c, so c equals 1. The equation of the curve is y squared times x equals 1. This example shows how to use the section formula to set up the differential equation, a valuable technique for IB problems. Now let's shift our focus to our second main topic, logistic growth. This is a fundamental model in biology, economics, and other fields. Logistic growth describes a population that initially grows exponentially, but then levels off as it approaches a maximum value or carrying capacity due to limited resources. Think of a population of animals in a forest with a finite amount of food. The graph of logistic growth has a characteristic S shape. It starts with slow growth, then accelerates, and finally decelerates as it approaches the carrying capacity, which we denote by A. This behavior is governed by a specific differential equation. The logistic differential equation is dp/dt equals k times p times the quantity, 1 minus p over a. Here, P is the population, T is time, A is the carrying capacity, and Ka is the growth rate constant. Let's break down this equation to understand why it produces the S-shaped curve. The equation has two main factors. The first, Kp, represents exponential growth. When the population P is very small compared to the carrying capacity A, the term 1 minus P over A is close to 1. So dP dt is approximately Kp, which is the equation for exponential growth. The second factor, 1 minus P over A, is the limiting factor. As the population P gets closer to the carrying capacity A, the term P over A gets closer to 1. This makes the entire factor 1 minus P over A get closer to 0. As this factor approaches 0, the growth rate dP dt also approaches 0, causing the population to level off. The logistic equation is separable, but solving it requires a technique called partial fractions. Let's walk through the general solution. First, we separate the variables. We get dP divided by P times 1 minus P over A equals K dt. To integrate the left side, we need to use partial fractions. We can rewrite the denominator as A minus P over A. So the integral becomes the integral of A over P times A minus P dP. We can decompose this into partial fractions, A over P plus A over A minus P. Now we can integrate. The integral of 1 over P is ln now P few. The integral of 1 over A minus P is negative ln A minus PR. The integral of K is Ket, so we have ln mil P phi minus ln A minus Pe equals Kt plus C. Using logarithm properties, this simplifies to ln P divided by A minus P equals Kt plus C. Exponentiating both sides gives P divided by A minus P equals B times e to the power of Kt, where B is a constant. Finally, we solve for P. After some algebraic manipulation, we arrive at the general solution for the logistic equation. P equals A divided by the quantity, 1 plus C times e to the power of negative K. This is the formula you will use to solve logistic growth problems. Let's apply the logistic growth model to a concrete example. This will show you how to use the general solution we just derived. Consider the population of an island P, which is currently 154. Its growth rate is given by the differential equation dPdt equals 0.16 P times 1 minus P over 500. We need to find the population after 10 years, the time it takes to reach 480, and the limiting population size. First, let's identify the parameters of our logistic model from the given differential equation. Comparing our equation to the standard form, dPdt equals Kp times 1 minus P over A, we can see that the growth rate constant K is 0.16, and the carrying capacity A is 500. The initial population, P at time t to 0, is 154. Now we can use the general solution formula. The general solution is P equals A divided by 1 plus C times e to the power of negative Kt. Substituting our values for A and K, we get P equals 500 divided by 1 plus C times e to the power of negative 0.16t. Next, we use the initial condition to find the constant C. We know that when t is 0, P is 154. Plugging these into our equation, we get 154 equals 500 divided by 1 plus C times e to the power of 0. Since e to the power of 0 is 1, this simplifies to 154 equals 500 divided by 1 plus c. Rearranging to solve for c, we get 1 plus c equals 500 divided by 154. So c equals 500 divided by 154 minus 1. This gives us c equals 346 over 154. Now we have the complete equation for the population p as a function of time t. It's p equals 500 divided by 1 plus 346 over 154 times e to the power of negative 0.1xt. With this equation, we can answer the questions. First, to find the population after 10 years, we set t to equals 10. Plugging this into our equation and calculating, we find that p is approximately 344. So, after 10 years, the population is about 344 people. Next, to find the time it takes for the population to reach 480, we set p equals 480 and solve for t. This involves some algebraic manipulation and using logarithms. We find that t is approximately 24.9 years. Finally, to find the limiting population size, we consider what happens as time t approaches infinity. As t gets very large, the term e to the power of negative 0.16 t approaches 0. This leaves us with p approaching 500 divided by 1, which is 500. This confirms that the carrying capacity A is indeed the limiting population size. Let's work through one more logistic growth problem, this time involving a chemical reaction. This will reinforce the process and show the versatility of the model. In a chemical reaction, the number of active molecules, N, grows according to the differential equation dm/dt equals Kn times 1 minus n over 10 to the power of 30. We are given that initially, at t0, there are 200 active molecules. After 10 to the power of negative 5 seconds, there are 1.5 times 10 to the power of 7 active molecules. We need to find the time it takes for the reaction to be 99% complete. First, let's identify our parameters. The carrying capacity A is 10 to the power of 30. The initial population N0 is 200. The growth rate constant K is unknown and we'll need to find it. The general solution for N is A divided by 1 plus C times E to the power of negative KT. Substituting A, we get N equals 10 to the power of 30 divided by 1 plus C times E to the power of negative KT. We have two unknowns, C and K. We can find them using the two initial conditions provided. Using the first condition, N0 equals 200, we find that C equals 10 to the power of 30 minus 200 divided by 200. This is a very large number, approximately 5 times 10 to the power of 12. Now we use the second condition, N10 to the power of negative 5 equals 1.5 times 10 to the power of 7 to find K. We substitute this into our equation along with the value of C we just found. After some algebraic manipulation, we find that K is approximately 1.2 times 10 to the power of 12. So our complete equation for the number of active molecules is N equals 10 to the power of 30 divided by 1 plus 5 times 10 to the power of 27 times E to the power of negative 1.2 times 10 to the power of 12 times T. The final question asks for the time when the reaction is 99% complete. This means the number of active molecules N is 99% of the carrying capacity, A. So we need to find Tt when N equals 0.99 times 10 to the power of 30. We set our equation equal to this value and solve for T. This again involves algebraic manipulation and logarithms. We find that T is approximately 1.2 times 10 to the power of negative 4 seconds. This shows that the reaction is very fast. Let's recap what we've covered. We've seen how to translate geometric properties of tangents into differential equations and how to solve them. We've also explored the logistic growth model, its underlying differential equation, and how to apply its general solution to real-world problems. Now, to help you master these concepts for your IB exams, here are 5 practice questions. I encourage you to pause the video and try to solve them on your own before looking at the solutions. Question 1. The tangent at any point P, xy on a curve cuts the y-axis at Q such that the distance OQ is equal to the distance PQ. The curve passes through 2, 1. Find its equation. Question 2. The tangent at any point P, xy on a curve cuts the x-axis at A and the y-axis at B. Given that AP equals PB and the curve passes through 1, 2, find its equation. Question 3. A population P grows according to the logistic model dP by dt equals 0.05 P times 1 minus P over 1,000. If the initial population is 200, find the population after 20 years. Question 4. For the population in question 3, find the time it takes for the population to reach 800. Question 5. A rumor spreads in a town of 5,000 people. The rate of spread is proportional to the number of people who have heard the rumor N and the number who haven't. If 10 people start the rumor and 100 have heard it after 1 day, how many people will have heard the rumor after 2 days? Welcome back. Let's go through the solutions to the practice questions. For question 1, the condition OQ equals PQ leads to the differential equation di EX equals Y over X. Solving this gives Y equals KX. Using the point 2, 1, we find K equals 1/2, so the equation is Y equals X over 2. For question 2, the condition AP equals PB means P is the midpoint of AB. This gives the differential equation di dx equals negative Y over X. Solving this gives Y equals K over X. Using the point 1, 2, we find K equals 2. So the equation is Y equals 2 over X. For question 3, we use the logistic growth formula. The carrying capacity A is 1,000, and the growth rate K is 0.05. The initial population is 200. We find the constant C is 4. The equation is P equals 1,000 divided by 1 plus 4 times e to the power of negative 0.05 t. Plugging in t equals 20, we find the population is approximately 475. For question 4, we set the population P equal to 800 and solve for t. This gives t equals 20 times the natural logarithm of 16, which is approximately 55.5 years. For question 5, the problem describes a logistic growth model with a carrying capacity of 5,000. The differential equation is dn dt equals kn times 5,000 minus n. The general solution is n equals 5,000 divided by 1 plus c times e to the power of negative 5,000 key. Using the given conditions, we find c equals 499 and k is approximately 0.000218. Plugging in t equals 2, we find that approximately 700 people will have heard the rumor. I hope this video has provided a clear and rigorous explanation of these important differential equation applications. Keep practicing these types of problems to build your confidence for the IBAA HL exam. Thank you for watching Dart Tutors.